Okay, I guess it's 11 sharp. At least it's 11 in Lviv, and it's 11 o'clock in Tartu as well. So I'll start. I'll start slowly for people to have time to chip in. My name is Dmitro Fishman, and this is a lecture on ensemble learning. I'm quite excited to give a talk about ensembles. And I'm also excited to be part of the summer school, Lviv Data Science Summer School 2020, which is the first Lviv Data Science Summer School which happens online due to foreseen and understandable reasons. This format has given us both a joy and trouble. So we do lack physical contact with people, with learners in the class. But at the same time, we were enabled to widen up the audiences and invite more people in. So we are pretty happy about this. And thanks to the organizers, we were, so this summer school has been made free, and this has opened frontiers even further. Just to give a couple of, just to say a couple of things about the lecture itself. I think that the topic of ensemble learning is somewhat underrepresented among the topics on machine learning conferences and summer schools. That's probably the reason why I decided to actually have this lecture, because I think ensembles are very powerful techniques and they are used in practice a lot. I personally use ensembles a lot in practice. And that's why I thought that ensembles are worthy subject to be discussed. So this is going to be a very practical, practice-oriented lecture. I'm going to tell you about different types of ensembles, how they are built. And I'm going to use very simple examples to illustrate the basic key principles of these ensemble techniques. I have another monitor to check out the questions that you might be asking over the Slido. So please do feel free to write your questions, because I'm keeping my eye. Well, one part of my eye is on the question board, so I can basically answer your questions at any time. So this lecture is very large. It's vast. It has a lot of material to cover, and that's why I would say that let's keep the expectation bar realistic. I have also a collaboratory notebook associated with this lecture, which has a lot of Python code and practical exercises that help you to practice the theory that we will see in the lecture. But also I have a Kahoot quiz. So both of these things we would get to if we have enough time. So let's not have high expectations. Let's try to go through the material in a very decent pace. And then if we have enough time, we could always jump into the code and still have a Kahoot exercise, Kahoot quiz. So a couple of words about myself. I am working at the University of Tartu, Institute of Computer Science. On the background, this is the place where I am right now physically located. This is called Delta Center. This is a home for four different institutes of University of Tartu, including the Institute of Computer Science. So this is where I am right now. And I'm also part of the Bioinformatics and Information Technology Research Group. So I'm also doing I do research. So shortly about myself, so my name is Dmitro. I'm originally from Ukraine. I graduated from the National Technical University of Ukraine with my bachelor degree. I moved to University of Tartu, and I became a master student of software engineering master program. And this was a master program which was run in cooperation with Tallinn Technical University. And during my master's, I took the exchange semester at Royal Institute of Technology, which is KTH, Karolinska Tehnika Högskolan. And now I'm a PhD candidate, so hopefully soon graduating with my doctorate in information technologies. And this lecture that I'm about to present is a lecture which is part of the machine learning course, which I teach in 3 different universities. So this fall, I'm going to give this machine learning course and including this lecture as part of my machine learning course in University of Tartu. And I have already delivered this lecture and this course as part of the machine learning course in UCU, Ukrainian Catholic University, and Kiev School of Economics. Couple of words about Tartu. So this is a small town in the south of Estonia, which is a northern, very small country in Europe. If you have never been there, I really suggest you to check out. Once the situation with COVID settles down and we are all happily safe from this disease. So Tartu is called City of Good Thoughts. This is a very special place with a very special environment, which somewhat provokes the great ideas and exploration and science. So I really suggest you to give it a try. And this is the Delta Center. This is where I am right now. I'll give a couple of words. I'll say a couple of words about University of Tartu and studying at the University of Tartu after the lecture. Now a couple of words about my research. So my research group, Bioinformatics and Information Technology Research Group, which I am one of the members. It is basically a group of enthusiasts. I would say computer science enthusiasts, which apply computer science, various kinds, advanced algorithms, various machine learning methods, software development tools to help biologists and doctors treat diseases. So myself, I had a dream to be a doctor at some point in my youth. And then I had very little choice with respect to universities which offered a very good medical or biological education. So I chose computer science. But later in my years, I figured out that there is a way to make a difference with respect to diseases being a computer scientist. So this was no brainer from my side. I have been full into this bioinformatics community. So you can check out this website if you want to know who we are and what we do. Couple of words about my projects. So one of the projects which I consider to be very illustrative as to what kind of things mathematicians with machine learning and deep learning knowledge can do is, for example, looking at the microscopy pictures and identifying cells on those pictures. So this is a project which we run in collaboration with a company called PerkinElmer. They provide us with a lot of imaging material, and we built methods that machine learning and deep learning, to be precise, methods to work with microscopy images, with microscopy data. One other project, which is a little bit off the track, bioinformatics track, is about self-driving, is about autonomous driving. Here's a project car. So this is the project with the title Autonomous Driving Lab, which we run in cooperation with Bolt company, which probably some of you may know. This is a taxi company, a taxi sharing company. And the idea of the project is to check out what are the state-of-the-art autonomous driving technologies that exist up there that companies like Bolt can use to make their fleet self-driving. enable self-driving fleets. So we are the ones to go through different technologies and try to implement them and see which ones are at the maturity, at the good maturity level that enable self-driving at low cost. Here's one interesting image. It's basically our crew, our autonomous driving lab crew, using joystick to drive the car through the drive-by-wire module, which is basically a toy to test the car, to test if the self-driving works, in the sense that there is this drive-by-wire mode, which allows us to pre-program the trajectory of the car, and to test that it works, you use something like this, like a joystick. So this is just to entertain before the meat of the lecture. So these are the types of research projects that we run at the University of Tartu. If you're interested in some of these things, you're very welcome to check out my SlideShare, which is slideshare.net/Fishman, and check out other lectures on similar topics, which I described, and see if you can find something interesting. Or if you want, you can connect with me on Slack and ask for more specifics. Now we finally move on to the meat, to the central part of the lecture, and a little more motivation as to why it is important to learn, to know things about ensembles, why ensembles make a difference, why they matter. We all know a range of different machine learning models. For example, just to give a couple of examples, for example, here's a k-nearest neighbor algorithm, which predicts a class of the point based on the classes of the nearest neighbors. Or here's a decision tree algorithm, which based on the question, based on the condition, assigns classes. Or all known and very famous neural networks, which are basically a connection of computational units in parallel that compute very complicated mapping functions. So these models, they can be, so we can join their forces. We can somehow combine their powers into one big model, which we call ensemble of machine learning models. The interesting thing is, it turns out that usually ensembles are more powerful than any individual model, or most of the individual models, right? So ensemble usually beats individual models because they are more powerful. And this is one of the major reasons why we use ensembles a lot, is that because they usually give us an advantage with respect to power. There are different types of ensembles. For example, this ensemble is clearly composed of models that are very different. So we have k-nearest neighbor, decision tree, and neural network. But you can have, so this is the ensemble of different models, but you can have ensemble that consists of same models, right? You can have ensemble of decision trees, for example. You can have ensemble of neural networks. You can have ensemble of linear regressions, and so on and so forth. So there is a flexibility, certain level of flexibility as to what is it that you prefer to make your ensemble of. There is also a flexibility with respect to how much you trust each of the models that are part of the ensemble. For example, if we consider this ensemble, where this is basically like an egalitarian world where you trust each of the models equally. It's a idea that every model performs at its best, and you should treat the outputs of each model equally. While there is another type of ensembles where you can say, well, I trust this model more than the other model. For example, I trust John I don't trust Sandy and Peter. I trust John more than the other two. So this is what we call a weighted ensemble, where I have weights or coefficients assigned to each of the models. And I also have, on the other side, there is a majority vote ensemble, where I treat every model's predictions equally, right? I also have parallel or sequential ensembles. So you could, for example, train models in parallel. You can feed the same inputs to each of the models, and then you can combine their predictions in some way. Or you can have a sequential ensemble. So you could fit the input in one model. You can take the output of this model and fit it as input to the second model, and so on, right? So you can have a sequence of models. You can have a sequential ensemble. So you can see that there are lots of ways how one can make ensemble. You can still have, for example, sequential ensemble that consists of many different models. You can have them, you can trust them differently. You can assign weights to these models in each of the ensembles. And this gives a rise to a large diversity of different things that we can test. So this is the outline of our lecture. This is a short overview of what are the things that we're going to discuss. And now we're going to just one by one rip off this gaps, rip off these labels, and a look inside each one of the topics here. And without further ado, and since you don't have any questions on the Slido, I will venture into the ensemble learning world. So Avengers Ensemble, we will now take a look on how do we make out of this very good models, we will make one super team that will fight all the problems in the world. For that, imagine that we have imaginary data set. Imagine that you have imaginary, which consists of 5 points in 2-dimensional space. All right, we have x-axis and we have y-axis. We have, so basically what we're trying to do, we're trying to predict y value of the point from its x value. We will separate this data into training and test set. We will extract the test points from the training points. So we will separate them, and we will hide the test points for now. Now what we will do is we will train 3 different linear models on the training data, right? So we will use multiple models, and we will use linear multiple models. For example, we will use a linear regression, which has this equation right here. And then we will use a model which has a L2 regularization, which is called ridge regression. And this is its equation and the line, the red line. And then we will use a lasso regression, which has L1 regularization. And this is its equation and the line and the corresponding line. Now these are the 3 different linear models that we trained on this very small toy example. Now we will bring back the test set, which contains 2 points, point 1 and point 2. And we will apply each of these models on this test set, right? So we can imagine like we have 3 different test sets, but it's the same test set, just visually made different. Now we will project each of these lines and their corresponding equations to the test set. So let's see how it would look like. These are our linear models projected on a test set with the corresponding equations. And what we are going to do right now, we are going to look at the predictions of each of the models for each of the points. So we have point 1 and point 2. And we are going to evaluate the predictions of each model for each of the points. Here's an example. We take a linear regression, and then we take X values of the test points. The X value of the test point 1 is 2, and X value of the test point 2 is 5. Basically, this is X values of the first point and X value of the second point. Now what we do is we take X values and we substitute X in the equation of the line with the value. And then we just compute what's the prediction of the linear model. So the prediction of the linear model for the first point is about 318, right? So we write this value right here. This is the value of y-axis that is predicted by the linear regression for the first point. And the same we do with the second point. We take 5, we substitute X with 5, and we calculate the value. This is what we do. And 5.55 is the value that we predict for the second point, right? So this is what linear regression thinks the y value of the second point is, right? 5.55. Now we do the same thing for ridge regression and lasso regression. Okay. Now, as in we are talking about ensembles, how does it fit into the topic of ensembles? Well, here are the predictions of each of the individual models, but we will be looking at the averages of these predictions. So here's the fourth model, and the fourth model is an ensemble, the average ensemble of these three models. To get this ensemble, to build this ensemble, we take predictions of each model and for each point, and we average them up. So here's an example. We take, for the first point, to predict a value using ensemble, we take the predictions of each individual model and we average them up, right? So this is the value that we get. Then we do the same operation for the second point. We get 4.89. And these are the predictions generated 3.32 and 4.89. These are the predictions generated by the ensemble of three linear models. So we generated an ensemble. And the true values are 4 and 5, right? So the true y values of the first and the second point are 4 and 5. I will not calculate the error function, which could be something like MSE or RMSE, whatever have you. We could still see that this average ensemble performs better than each of the individual models. And this is called basic ensemble, right? By the way, just to remind you that you can ask questions on Slido, and I will be very pleased to answer these questions. Just to remind you, I'm keeping an eye on these questions. I have a separate screen dedicated to this. So we looked at so this is the way how you built a very simple ensemble for a regression problem, right? So when we try to predict a continuous value instead of classifying the classes, this is how we do it. If we're facing the classification problem, we can use a very similar trick, right? So here's our training data, which is if somebody of you knows that this is CFAR10 images, cats and dogs. So there are two classes, cats and dogs. So we are dealing with a binary classification problem here. And there are three different deep neural networks. They are actually looking very much the same, but due to random weight initialization and data partition, these trained models turned out to be slightly different, right? So as we have trained these three models, we can test them using a test image of a dog. So this is a test image of a dog. We feed this image into each of the models. So we feed it into model 1, 2, and 3, and we record its predictions, right? So the first model, looking at this image, says it's a dog, right? And we record that this is a dog for model 1. The second model also thinks it's a dog, So we record a dog for the second model. But the third model, looking at the image, thought that this is a very nice, cute cat. So we record cat for the third model. In order to build an ensemble, we do something called majority vote, right? The majority voting. Basically, we are counting the number of times each one of the classes has been predicted. In our case, it's very simple. It's 2 times class dog and 1 time class cat. And then we take the majority as a prediction generated by the ensemble. So the ensemble is this abstract model that exists above the normal models, which take the predictions of individual models and makes a separate independent prediction based on these predictions. So in the case of majority vote, you just output the prediction that had been mentioned most of the times by individual models. So coming back to our outline of the lecture, this is the first label that we rip off. This is the simplest, this is the basics, that's the foundation of ensemble learning, right? We have ensemble learning for regression, we have ensemble learning for classification. In the first case, we take the average of predictions. In the second case, we take the majority vote. So there is a question on Slido. Thank you for using the Slido. And the question is, the basic ensemble that I was showing, right? So this one with the dogs and cats, and basically the average one as well, is a parallel ensemble. And yes, the answer is positive. These are the examples of parallel ensembles. We will check out how the sequential ensembles look like in the second part of the talk. But these are the examples of parallel ensembles, exactly. So thank you very much, Anonymous, for your question. And there is somebody who has upvoted the question. And there is another question. I'm looking at this right now. So so the question is a bit longer, but it basically says, so somebody has ensembled 2 deep neural networks and it performed worse on the training set than both of them individually. So the ensemble worked worse. The performance was not as good as for each of the models individually. So the question is basically, the question is to my claim that usually ensembles outperform individual models. Indeed, it's not always the case. It's not the case in 100% of the time. Sometimes ensembles do perform worse than individual models. And in my practice session, we do have these kind of examples. And the case why this could be happening is that you ensemble, or in other words, you aggregate predictions of models that are vastly different in performance. So let's say you have a very, very good model that you ensemble with very poor model. Then if the model is sufficiently poor, then the ensemble performance will be something in between of this super good model and very poor model, which would end up being poorish, right? So not too good, worse than the one that was performing better. So sometimes it can be happening. And also another one is, of course, you need to practice attention to the way how exactly you build those ensembles. Here I'm basically showing classical ways to build different types of ensembles. And most of them would perform better than the individual models. So I'll answer another one and then we will proceed with weighted ensemble. So Olga is asking, what is the general logic behind combining different types of models? How it should be connected with the task? So how do I know, so my interpretation of the question is, hopefully correct interpretation of the question, is how do I know which models should I combine when I build an ensemble? This is a very good question. I don't think there is any bulletproof answer to this one. I think you try to combine models that are fast, because ensemble is going to be slow by definition. There are lots of models, so you're interested in efficient ensemble, and at the same time, still powerful enough to have different predictions. So you are interested in models that are diverse, that do have different predictions. So it would not make sense to combine models that are having absolutely the same predictions. And we are going to talk about how do I make the models diverse. And also you take technical convenience into account. Sometimes it makes sense to combine the same type of models because they require the same type of input. Sometimes you might want to go for different types of models because you know that different types of models of that specific kind, they look for different types of features. So it might be a good idea to combine models that learn different kinds of useful features, so that your combined model, your combined ensemble, would pay attention to all these features. I will leave the other questions for now in the chat, and I'll return to questions. So if you could, please upvote the questions that you like, so that by the next stop, I have the top 3 upvoted questions that I'll be picking and answering. Thank you very much for asking questions. So in that way, I feel and I know that you guys are watching and there are questions, so it makes sense to continue. Great. So, so far we have been discussing ensembles which are egalitarian ensembles, which means that they are equal, meaning that we trust each one of the models equally. We think that, well, I hope that John, Sandy, and Peter all have the same capacity, the same learning capacity to kind of solve the problem at hand. But it turned out that not all models are equally useful, right? So if we look at the majority voting ensemble, by combining predictions of different models, meaning that we count dog, dog, cat, we assume that each model is having equal confidence and equally good at predicting dogs and cats from the images, right? But the question now is, are they really equally useful, or is this just an assumption that may not be true? We cannot really use the test set to evaluate this question, to evaluate this hypothesis if the models are equally useful, because if we use test set, then we wouldn't be able to kind of use the test set again in the future to get the unbiased performance of these models, because the models would already see test set. We would pick the best model based on the test set performance. So the test set performance wouldn't be adequate. This wouldn't be adequate anymore. So we don't want to use test set. We want to use only training data. So what people use in practice is cross-validation algorithm. They assess the performance of the model and comparing the model performances on the cross-validation algorithm. So what do I mean by this is that, for example, we select out the model number 2, for example. We take our data, we split it into folds, fold 1, 2, and 3, and then we train a model 2 on different combinations of these folds. So fold number 1 plus fold number 2, fold number 2 plus fold number 3, and fold number 1 plus fold number 3. And we use the remaining fold as a validation set. So this is a 3-fold cross-validation. We obtain some scores for each of the folds. And then let's use some fairly realistic scores for each of these validation scores. Let's say 75, 70, 65. And then to obtain the general estimate of how good the model works on that kind of data, we just average them up, right? So we just take the average, and this by coincidence, this is going to be 0.7 for the model 2. So this is the average assessment of how well the model performs on the given data. All right, so this is somewhat our approximation of how well we think the model is in general for this type of task. We get similar types of scores for the other two models, 0.61 and 0.57. And these are the absolute values, right? We can make them sum up to 1 if it's more convenient. We can calculate the sum of these scores. This is 1.88. And then we can divide each one of the weights by the sum. But this is not necessary. This is completely unnecessary. You can leave these absolute scores and this everything would be fine. It's just for our convenience. So now we have this relative weights for each model. You can see that model 2 is more important, or so we think, for this decision than model 1 and model 3. And maybe it makes sense to trust model 2 predictions more than we trust model 3 predictions. But let's see, what does it actually mean in practice? Imagine yourself a parliament. Parliament has deputies and parties. So let's imagine that each model is supported by its party, and the party consists of deputies. And there are as many deputies as the score of the model. So if it's 0.33, there are 33 deputies that support the model. So these are the representatives or deputies, whatever. Imagine the ensemble parliament. So here's the ensemble parliament, which has 100 seats in total. And these parties, they occupy seats in the parliament. So for example, we have 33 seats taken by the Model 1 representatives, 37 by Model 2 representatives, and 30 seats taken by Model 3 representatives, right? And there are 100 seats in total, right? So each of the models occupies its own place in the parliament. And then one image or images from the test set are shown to the parliament of ensemble parliament. And then each party votes. And party votes as one team. So there are no deputies that vote differently. Every deputy of the party vote the same. And they vote for a class that they consider to be true. Okay. So what has been happening previously with the egalitarian ensemble, we just had one vote per model, right? So model 1 had one vote, model 2 had one vote, and model 3 had one vote. They all combined together with the majority vote. We would have 2 dogs predicted and 1 cat, right? So we would say, well, it is just dog because it has majority vote. In the case of this weighted ensemble, we take into account the relative weights. And we look at how many deputies voted for a certain class. For example, in the case of model 1 voting for dog, then 33 would vote for dog, 37 would vote for dog, and 30 would vote for a cat. We would have 70 votes for dog and 30 votes for a cat. In this very specific case, nothing changes because the outcome is still the same, right? The dog has been upvoted in both cases. It doesn't really make a difference. Where it does make a difference is when we have more classes and we have a tie. We have a draw between different models. For example, let's consider a case when we have 3 classes, dog, cat, and rabbit. And the basic ensemble would laid out to be equally distributed between classes. So model 1 would vote for a rabbit, model 2 would vote for a dog, and model 3 would vote for a cat, right? Well, and the same would happen for the weighted ensemble, but now that we know that we need to trust model 2 more than model 1 and 2, model 3, then we would know that dog has more votes than the other 2 classes, which means the dog would win. While in the first case, where there are 3 different answers by 3 models, we would not have any specific thing to go for, since there is no class that has a majority. We would need to toss a coin or roll a die between the different classes and see which one wins. So this is definitely something that is unwanted, and we would prefer some definite answer. So the second case with a weighted ensemble provides us with a definite answer, we definitely know that we should trust model 2 more than the other 2 models. And since model 2 votes for dog, we vote for dog. This is a type of democracy, right? So Winston Churchill's quote that democracy is the worst, except of all the rest of the structures that they have tried in the past. So this was basic ensembling first. Then we moved into the weighted ensembling. Now I'm checking out your questions. So hopefully there are some questions up here. So the first upvoted question goes like this. Instead of majority voting, we can average predictions before applying softmax for linear models, or before applying the threshold in random forest. Is majority voting better than this? So basically the question saying that we can treat the normal classification problem as a regression problem, because most of our models, they predict a probability score or some certain score like SVM or any other model. So they usually predict a score for each of the class, right? Instead of saying that this class. Indeed, we can take the average. I think it's just sometimes more convenient to think about this as an, if you have more than 2 classes, you have multi-class classification problem, then it's just inconvenient when you average them up. You can still do it. You can still average up the scores of different classes, and then you can normalize them so that they are sum up to 1. I think this is an approximation. I think average is better in that case. I think average is better in most of the cases. In fact, I think if you have an ability, if you have a possibility to use average instead of majority vote, I think it would make sense to go for it. A majority vote is an approximation and abstract idea to look for. When one model votes for dog, the other votes for dog, and third one votes for cat, you choose dog as a result of this. The second question I already answered. This was about basic ensemble being the parallel ensemble. So both of these, all 3 cases right here are the parallel ensembles. Could you give an example, please, of data where lasso regression is weighted more than linear regression? I cannot give you the example right now. I used the example of linear regressions, different types of linear regressions, just to show that there are different models. I'm not aware of the specific example where lasso would be weighted more than the other 2 regressions, but you're welcome to play around with different methods and different examples and see for yourself if there are any cases where lasso regression can be upvoted than the other 2. I don't see right now a reason why it can't be with a higher weight than the other 2. I do think that it's possible, but I don't have any specific example at hand right now. I just used the lasso regression as an example of different types of model, just different kind of model. Would we be covering common pitfalls of ensembles in the lecture? Yes, we will. I'm going to talk about common pitfalls such as long running time and a complex model at the end of the lecture. Yeah. So are there any asymptotic results predicting convergence of prediction to the true value with a higher number of models? In fact, I think there are such things. I think there were proofs showing that under certain, there is a very common problem called 3-judge problem. If you Google 3-judge problem, you will stumble upon a logical problem where there are 3 judges on one side and 1 judge on the other side, and then you're given probabilities with which judges, not the probabilities, but accuracies of each judge. And then you are given a question whether you would go to 3 judges, where one of the judges is basically tossing a coin, or you would go to 1 judge, which is better than random. And then you're asked to say which case you would attend to. And with the mathematical formulation, you can actually see that after some accuracy of the 2 judges, you better go to the 3 judges, although one of them is basically a random guess, right? So it actually makes sense from the mathematical point of view using ensembles. There is a proof of that. Given that predictions are averaged, it seems that we need some predictions above and some below the true value to get something closer to the true value on the average. But how can we ensure that? So this question refers to my example with regressions, where I'm basically saying that average would perform better. So I have to admit here, this was a purely illustrative case. I made it up, so that all of you know, I made it up. I confess. So in reality, ensemble of linear models may not be really good because they are pretty linear, and we need more complicated models to account for different types of relationships between features. But use this as an example just to show how exactly the average ensemble is calculated and what do we call a basic ensemble. So please do not look for holes too strictly in my examples. There are definitely, and thank you for pointing these out, but this was just an illustrative example. So I cannot guarantee that this exactly the same principle is applied, but this was just to show that this is how basic ensemble works. So thank you for asking questions. Please write more questions. Currently there are 8 questions. I'm pretty happy to answer questions. So thank you very much for writing questions. And if I haven't replied to your question in full, please somehow reformulate the question so that I would understand what you mean by that. Okay, now we can move on. We soon have, so now we are talking about the diversity. So somebody asked, so how do I ensure that the ensemble would work nicely? So one of the answers to this question is you need to ensure that that the models that you are training are diverse, that they are different enough, that they are taking into account different features. Then combining these models would yield better results. This image is not very representative of diversity. There are too few female athletes, at least in the first row, but the idea is that you need to get the diverse crowds of problem solvers to really solve the problem effectively. So one of the ways to get the diverse models or diverse ensemble is to use very diverse models. For example, you can use deep neural networks together with decision tree and linear models. But this way is not the most convenient at all times because these models require different pre-processing techniques. They might need different shapes of inputs. They might predict different types of outputs and so on and so forth. So it's not always easy to combine these kinds of very diverse models. Sometimes we really have this one best or lucky model that we use for most of the problems, and we really want to make an ensemble using this one little model that we like. How do we go about this, right? So we do have just one model that is pre-trained, for example, on some data, and we don't want to change the model. We do want to get an ensemble, but we don't want to change the model. So what happens in that case, we can play around with the data. So instead of changing the model, we would look and change the way how data is structured. So here's our training data. And we take random samples from that data. So there are 6 images in this data. And let's say that we take 70% of the data into one of the samples, so-called samples, right? So we have 4 images. Then we take another sample, another 70% of the data, another 4 images. And then we take another sample, another 70% of the data, another 4 images. You can see that these samples, they can fairly well overlap. So they can be partially similar. For example, this little doggy here in the basket, it is actually present in all 3 samples. And this little doggy here, it's also present in all the samples, while the rest of the images are different between the samples. So this is called bootstrap data. And the process is called bootstrapping, right? So these are called samples or bootstraps. The process is called bootstrapping. So what happens is that we feed each of the bootstraps into the same model. We create 3 copies of the model, of the same model, and we train it using different bootstraps. And then they become different because you train the model on a different data, it gets slightly different or more different depending on how different the data is. So how is this bootstrapping, one may ask, is different from normal cross-validation, for example? Let's take a look. So in cross-validation, we split the data into non-overlapping folds. Like in this case, 2 images would constitute 1 fold. And then we would train the model using 2 folds out of 3. And we would use the 3rd fold, the holdout fold, as a validation data. So this is what the cross-validation does. In bootstrapping, there is no strict division into folds. So you saw that some of the samples, some of the bootstraps, they can overlap. And in bootstrapping, missing data is not used as a validation set. We just take the sample, we just randomly include some of the images, and some of the images we randomly exclude, right? So this is the difference between bootstrapping and cross-validation. After we have done the bootstrapping and we train the diverse models, because now we train them on different sets of data, we take the validation data or test data and we feed it into each of these models. And then we collect the predictions of these models. We combine these predictions. Again, we can use majority vote, or as somebody suggested, we can predict probabilities and then we can use the averaging. Again, the same stuff. We can use majority voting as well. And then we can, we generate the final outcome, final prediction. And in that case, it's a dog because there are 2 models that vote for a dog and the 3rd model that votes for a cat. So this step is called aggregation, right? So this is called aggregation. This could be both majority voting or averaging. It depends on what's your implementation. And if we combine this, so this combined algorithm, bootstrapping plus aggregation, is called bagging, right? Because it's a bootstrap plus aggregation. Right. So we, just to repeat, bootstrapping the data, we create bootstraps. And then each of the bootstraps is called bags, right? So each of the bootstraps, sample, bootstrap, or bag, they're essentially the same things, right? So we call them bags, and then you feed them into the models. So let me check out if there are more questions. There are no more questions. There are 8 questions as they used to be. So let's continue. So the concept of the bootstrapping, this concept that I have discussed just right now, the introduced bootstrapping, it very often comes with the decision trees. So it's very often used together with the decision trees. Let's remind ourselves shortly what the decision algorithm is. What is it that it does? The decision tree algorithm asks questions about the values of independent variables, about the values of independent variables to predict a class of the dependent variable. Consider this 2D example where we have x1 and x2. These are independent variables that are given to us, and the class variable, which is something that we want to know about the points that we have. You can think about this as height and weight of the person, of the individual, and the class would be, do they have diabetes or if they don't have diabetes, right? For example, BMI and heart pressure or something like blood pressure or something like this. And then the classes are the diabetes or no diabetes. And then the decision tree would look like this. it would ask a question about one of the independent variables, and provided the answer to this question either true or false, it would predict either 0 or 1, either red dot or a blue square, okay? Yeah, so now here's an example. For example, we choose to have a threshold of 4.5, right? So we're saying that basically, if the value of the x1 variable of the point is more than 4.5, then we say that this is a red dot. We can think about this as a person that does not have diabetes. And if the value of this variable x1 is less than 4.5, we predict this to be a blue square, or person with diabetes. So this is the decision tree that uses x1. Here is a decision tree that uses x2, the same concept. So we're asking question about the value of x2, and then we are classifying points depending on the value of x2 that they have. But we also can have two-level decision tree. For example, we can say that if the value of the point x1 is more than 4.5 and x2 is less than 3, then we predict this to be a blue point. While if it's more than 3, then it's a red point, and so on. So this is how the decision tree, in short, how it works. And now we will check out the way how bagging works. And we will learn 3 different decision trees for this in essentially a toy example, toy data set. So first step in bagging classifier, to building bagging classifier, bagging ensemble, is that we create bags, or we create bootstraps. So we take 80%, for example, 80%. I know that previously I told you that we take 70%, but it doesn't matter. You can choose it based on amount of data that you have. This is a hyperparameter that you can tune later on. So in this case, I choose to have 80% of the data that I select from my points, because it's kind of convenient. You have 5 points, 80%, it's 4 points, easy peasy lemon squeezy. So I have 4 points selected in my first bag. I have another 4 points selected in my second bag, and I have yet another 4 points selected into my third bag, right? So I have 3 bags with different points, right? Three different bags. What happens is that for each of these bags, I build a tree. So I take this bag, this is bag number 1. So this is not the entire data set, because you can see that one last point is somewhat shady. And this is because it's a bag number 1, which has just 4 points. So what is it that we do to build a decision tree? There are 2 steps, 2 major steps. One is that we need to evaluate all possible splits. So decision tree works on this conditions, on splits. And first of all, we find out what are the possible splits, all possible splits. Let's look at these lines here. So these are the possible splits with respect to x1. But we also have x2. So we can also have, we can have splits with respect to the other variable, which is x2. So we can have these splits as well. Now ask yourself another question and think about this for a second. Are all of these splits are reasonable? All of these splits are reasonable or not? And if you think about this a little, then you will see that some of these splits, in fact, these splits are not so reasonable, because if we use these splits in the decision tree, then one part of the tree will contain all the data points that we have, and one part of the tree will not have any points. So there won't be any points in the other half of the tree. So we want to avoid these splits. We only end up having these 4 splits. So this was the first step in the decision tree algorithm. We have identified all possible splits. Now, how do we evaluate all possible splits? So now we need to say how good is each split. Normally, people, when they introduce decision trees, they use something called information gain. Here, as this part of the machine learning course, I use something simpler. I use accuracy to define the goodness of the splits, to assess the goodness of the split. So what I do usually is that I say, let's calculate the accuracy for each of the splits in this tree. For example, let's focus on one split at a time. And let's assume that with this split, we predict that every point on the right is blue and every point on the left is red. And then let's calculate the accuracy. Normally here I stop for a second and then I stop bothering my students with questions. So how much would be the split? But since I don't have a direct access to you guys who will listen to this online, then I'll do it myself. So how do we calculate this value? On the right, we have 2 blue points, which we guessed correctly because we predict everything on the right of the split as blue point. And on the left of the split, we have 1 red point, which we predicted correctly as well, because we predict everything on the left to be red. So the number of correctly guessed points is 3, right? There are 3 points that we guessed correctly and 1 point that we did not guess, because the last point, this point, is not present in the back. So we're not considering this to be part of the decision tree. And that's why we have 3/4, which is 75%. So this is the accuracy of the split is 75%. Well, somebody can say, what if we, you're saying, let's assume we predict blue on the right and red on the left, but what if we do the other one? What if we predict red on the right and blue on the left? And this is totally possible. So we need to consider both of these options and calculate the accuracy for both of the splits. In fact, the good thing is we don't need to calculate it separately because the accuracy of the original split gives us the accuracy of the reverse split -1. So we need to subtract the accuracy of the original split to know what's the accuracy of the reverse split. So this would be 25%. We could differentiate between the splits by using arrows. So if the arrow is pointing up, then the blue part of the prediction is on the right side and the red part of the prediction is on the left side. If the arrow is pointing downwards, then it means that the red part is on the right. Now we have calculated the accuracies of the first split, and we need to calculate the remaining 6 accuracies, which seems like a lot at first, but you shall worry not. We do not have to calculate all 6, as we just discussed. We need to calculate just 3 because the other 3 are given to us by just simple mirroring. And in fact, it will be very simple. If we look at the second split, it's fairly easy to see that it's 50-50, right? Because we have both types of points on both sides of the split, which means that there are 50% on one side and 50% if we go for the reverse split. The third split is actually a mirror of the first split, which means that we have 25% on top and 75% at the bottom. So it's easy as well. And the remaining split is also 50-50 because it has both types of points on both sides. Easy. Right, finally, got it. Now that we have assessments or performances for all 4 splits that we consider to be reasonable, we can finally go to the second step of the algorithm, which is basically, let's choose the best split, right? So we choose the best split. And there are 2 splits to be considered, one and the other, and they both have 75% accuracy, which means that we are somehow having a tie here. And as I said before, ties in machine learning are usually resolved by tossing a coin, random generator, saying that which one we should keep. And we toss a coin and we say that, well, let's keep this one because why not, right? Because they are all equal. So we keep one of the splits. Here's the resulting tree. If we draw it like this, like a diagram, then we see that, well, if the value of x1 of the point is more than 4.5, we predict red class. If the value is less than 4.5 of the x1, we predict the blue class. Okay. Now the question might be, are we done here? Do we think that this is the job done and we are happy, or we can still do something? So if we look at the accuracies for each of the leaf nodes, so if we calculate the accuracy of both sides of this tree, so we see that on this side we are 100% accurate, but on this side we actually got only 2 out of 3 points correctly. And basically that means that we can still go on and improve the performance of the model by building the second layer, right? So we can just consider one branch of the tree, one part of the tree, and we can add one more split inside this branch to make the tree better. So let's consider that, and let's recall what are the steps of the algorithm. There are 2 steps. One is to look for all possible splits, and the other one is to choose the best split of the out of the ones that we considered. So there are 3 splits. There are actually 6 possible splits. And if we assess each one of the splits, meantime, I'm checking for you guys questions here. So there are a couple of new questions. So I'll go back to the questions as soon as I'm done with the backs. Okay. So we just assess the performances of each of the splits, and we choose the best one. So the assessment is that we have one split that has 100%, and we don't have any good contestants for this split. So we choose the split that provides 100% accuracy. Here's the final tree, and this is how it looks. So we have a tree for the back number 1, which has a 2-layer structure, which first asks if the value of x1 is more than 4.5. And then if it's not, then it asks if it's more than 2.5. And if it's not, then it predicts blue class. And if it is, if it's smaller than 2.5, it predicts the red class. Okay, so this is the tree that we obtain on the first back. Okay, this is how it looks. Great. So this is the decision tree for the first back, and then we built a decision tree for each of the backs, for each of the remaining backs. So here's the decision tree for the second back, and here's the decision tree for the third back, and then we combine them together by overlaying the decision boundaries, right? So we look at the remaining backs, the backs that we have, and we combine their predictions, right? So here we go. These are the predictions. This is the prediction of the first back. Then we add the prediction of the second back on top of the prediction of the first back. And then we add the prediction of the third back on top of the 2 previous predictions. Okay, now what happens is that we perform some sort of majority vote per segment, right? So we basically generate a majority vote per segment. And here we go. So we look at the first segment. We see that there are 3 red areas overlapping of this segment, and we can trace these areas to individual trees, right? So these are the trees that contributed these red areas to the final tree. And we can say, well, that it makes sense if everything that happens to be in this area of this X and Y location, then we call it a red dot, right? So this would be area of the red dots. Then we do the same operation for the next area, for the next place in the tree. And then we figure that there is 1 red area overlapping with 2 blue areas, and we can trace them to the original trees. And this means that this looks like we have to predict the blue class for the dots that will be that will fall into this area. We do the same for the remaining areas, and here we go. This is the back of decision trees. This is how we built backs of decision trees. I will now look at so this is our intermediate slides. So we looked at the basic ensembling, weighted ensembling, and bagging, right? So we looked at the way how we built bagging. Now let me check out the questions, if there are any more uploaded questions. It seems that there are mostly questions that I already answered. There is one more question was some math. It's fairly too long for me to read right now. What about out-of-bag estimation? Is it much worse than testing on completely new data? Sorry, it has gone somewhere. So is it much worse than testing on completely new data? No, it's out-of-bag estimation is fairly okay. So the person refers to the fact that to my claim that the missing data from the bootstraps, when we perform bootstraps, we do not use the left out data as validation data. No, in fact, we indeed do sometimes. I just wanted to leave it out from this class, but sometimes we do use it for the out-of-bag estimation. It's not much worse. It's definitely not as good as using a separate test set. And sometimes we can do it. It depends on what is our goal. But essentially, we usually still have a separate validation set for testing the individual models, or we just, or even the other way around, we just build the models using the training data, the sample that we have, and then we build the bag of trees, and then we validate the entire bag. And we can't use the out-of-bag because basically, if we build the entire ensemble, there is no out-of-bag for this ensemble. But indeed, you're right. Sometimes this missed data can be used as a estimation or assessment of model performance. So let me find some other question which was uploaded. I'm not sure where the other question has gone. So yeah, I guess I will, please do upload the questions that you're interested in so that I can check them out and see which ones seem to be most important. And then I will, I'll read from the top. But thank you for writing questions. Again, I just want to emphasize how important is it to keep track of the questions and have the connection flowing between the lecture and the questions. Okay. Right, so we looked at the basic ensembling, we looked at the weighted ensembling, and finally we looked at the way how bagging worked. Okay. Now I wanted to move into random forest algorithm. So we shall add a simple twist to the bagging classifier that we have examined so far. And this little twist will be in the way how we built the decision trees, right? So the way how exactly the decision trees are built. So as last time, we take the entire data set, which is 5 points, and then we do the resamples, 80% resample, 80% resample, and 80% resample, as we did before. So we generate 3 bags. So this is exactly as we have done before. And now we dive into the first bag, and something will change with respect to the way how we build the tree inside the bag. Okay, so it will require a lot more coin tossing, but let's see how exactly this will work. So to build a tree, we still use the previously referred 2 steps. So evaluating on possible splits, then choosing the best split. But this time we also have a new step. And this new step is to choose a random set of features. So besides choosing a random set of examples or instances for the bag, we also choose a random set of features. So in this very particular case, we had X1 and X2, right? So we had both X1 and X2. So there are only 2 features to choose from. Normally, so now we will just randomly choose one or the other, but normally we keep about 80% of the features, of the original features. And since I do have only 2 features here, I don't have a possibility to keep 80%. Otherwise, I would always, or most of the time, I would keep both features and nothing would change. So just for the example, for the illustration purposes, I will use 50% of the features, okay? This means that I will toss a coin, and when it falls heads, I keep x2, and when it falls tail, I keep x1, okay? So let me toss a coin and decide which one of the 2 I choose to keep. It falls heads, it comes heads, so I keep x2, okay? Otherwise, and I get rid of x1. Otherwise, I would get rid of x2 and I would keep x1, okay? So this would be the situation. Here's our back, and we only have x2 to decide the split, right? Now we evaluate all possible splits, and as you remember from last time, we now have only one split to choose, and they both are equally bad, right? They're both 2 arrows, 2 sides. They're equally bad because they are basically 50% chance, both of them. But we need to choose one of them anyway. So we toss a coin and we choose one of the splits here. Okay. So this is the tree. This is the tree. And for the sake of, in principle, we can go deeper, but for the sake of example, we will stop at this level. So basically, we'll just have class 1 and class 2 on both sides, and we will stop here. And also another important observation is that every time you would need to toss a coin to select a new random set of features. So every time you go deeper in the tree, every time you need to toss a coin. Every time you need to select a random set of features. Okay. So this is the way how the tree now looks like for the first back. So this is where we kept x2. We had a coin coming heads, so we kept x2. Let's build a tree for the second back. The coin fell tail, so we kept x1, and this is the tree that we built. And then for the third back, the coin came tail again, and we kept x1. So here is the tree. So there are 3 backs. Each one has a separate tree. And now, as in previous, in the case of backing classifier, we use this. We build this ensemble using all these predictions, all these trees. So we combine the predictions together. So let's see how this would work. We just overlay every prediction, and this is what we get. Okay, this is what we get. So one thing that you can point out is that this model is not perfect, is imperfect, because there is a red dot on the blue area. But this is because we use just 1 layer trees, okay? This is because we use 1 layer trees. If we would go deeper, most probably we would be able to classify our training set perfectly. Given 5 points, it's not so hard. Yeah, so it turned out that this approach of selecting features randomly for each node has been shown to produce great results in practice. This idea that you need to select the random features every time you shuffle, every time you create a tree, it's been shown to act as a regularization to some extent, and that has been shown to be able to kind of reduce the overfitting. And this is the algorithm called random forest. I would call the random forest as basically a working horse of the machine learning world currently. I think we use random forest a lot, quite often these days. Yeah, so just to remind ourselves what's the algorithm. So from several bags using bootstrapping, we built trees in a way that every time we descend into a node of the tree, we choose a random set of features. So it could be a root node as well. So if you descend into root node, you choose random set of features, then you descend in the other one, you choose a random set of features, and you choose the random set of features from the original set of features, not from the ones that you had in the beginning of the node. And then you merge the predictions using the majority vote or averaging, right? And that involves a lot of coin tossing, right? Okay, so far. So what we have seen so far, we have seen vanilla ensemble, where we take model predictions, we average their predictions, and we take that as a prediction. We have seen weighted ensemble, where we have coefficients, right? We have some certain coefficients. We have a parliament where models vote for the specific classes, and then we decide based on which class get most of the votes. We looked at the bootstrapping and aggregation. This is the algorithm that we named backing, that we called backing. We use bootstrapping to train different models. Then we averaged, aggregate the model predictions. Then we looked at the way how this backing is used with a decision tree classifier, but the truth is you can use it with different types of models. It doesn't have to be only decision tree classifier. It can be something else. Yeah, so we aggregate the predictions, overlaying the predictions of each of the individual models, and that's how we get the ensemble. And then the random forest algorithm. So every time we create a tree, every time we descend to the node, we choose a random set of features. So this is basically backing plus random feature selection, which gives us random forest. You get forest of random trees, right? And this is the fourth topic and fourth tag that I want to rip off and show. Let me check out the questions. Let A be model one. So again, I think that this could be a good, I will check this question during the break, because I don't think I have enough capacity in my brain to focus on something more sophisticated like this right now. It's the first upvoted question right here. Yeah. So there is one question by Anonymous that I have already answered. Said he asked about so is it in bootstrapping or in cross-validation where there is a more risk of biasing the data, right? So said he is asking which one, right? Bootstrapping or cross-validation, which one gives away more kind of information about data? I think it's a good question, but I think another kind of way of looking at it is that these algorithms are used for different types of purposes. So the cross-validation algorithm is usually meant to assess various models. So we usually apply cross-validation algorithm in places where we want to know which model performs best, right? So you have a set of models and then you would like to choose which one works best. So you run cross-validation algorithm. In bootstrapping, we use bootstrapping to produce a training data for different types of, or for the same type of model. So I would say that they have different purposes. I would say that cross-validation is not 100% safe in the sense that when we validate, we train, we validate, so it kind of is safe, but you use part of the data as a training data and the part of the data as validation data. If you are being careful and you're not retraining the same model across different folds, then all be fine and you should not have any problems. Although there is one problem that this training data can be too small and you can be largely overfitting and getting very shaky and unstable results. So this is one problem with cross-validation. With bootstrapping, I think it's also fine. So you train individual independent models. So I would say that with the care, if you apply enough care and you being attentive, then none of these models, none of these methods actually bias the data. Well, in a sense, you would need your test set, separate test set anyway, to somehow assess the performance of the model. But of course, if you first do the bootstrapping and then cross-validation on the same data, this is not going to be good. It's not going to be adequate. Yeah, so there is another question about basic ensemble parallel. This one we have already answered. Lasso regression, pitfalls of ensembles, yes, later in the lecture. Yeah, so I basically answered all but first question. So let me read the first question, since we have this online stream, and I think it's fine to submerge a little. So let A be model 1 prediction and B be model 2 prediction. You are talking about ensemble 0.8 times A plus B 0 times 0.2, right? Well, it is kind of ensemble that I'm talking about. There is one problem here. If you have such uneven coefficients of the models, meaning that your first model is like 0.8 and the other one is 0.2, I would be suspicious that these models are nice in the sense that B model is actually necessary. Can we try ensemble 1 times A minus 0.2 times B divided by 0.8? So negative weight, instead of having positive weight, talking about negative weight. I encountered this negative weights in the ensemble when I made a new training data by predicting of my 7-8 CNN, then logistic regression gave negative weights. I think you can use negative weights, although I have to admit, I have never seen that before. This means that one model is counterproductive. It means that it's malicious. It's trying to destroy your performance. It's learned a worse way, or the way that it's not supposed to work. I assume that it can be possible. I would not see how this would be possible if all the training is done properly, but I assume that this is possible. For example, if you haven't trained enough, or you have trained with the wrong objective, or the model has overfitted significantly. So I assume that this would be possible. This is a very good question. I do recognize, I will put my finger on this question because I think it's very good. So I would say that this is possible. The schema that you have pointed out is possible. I think it's a nice thing to think about. So yeah, thank you for asking this question. Do you guys have more questions? Okay, there is one more question. Does decision tree algorithm work with boundaries of more complex shapes than straight lines? So the question is, I don't know who asked this question, but he or she gets my like as well, because I think it's a very good question. So now it should be repurposed and it should be made higher on top. So the question is here, if you guys look at the decision boundaries here, right? So for example here, so this decision boundaries are linear, meaning that we have a simple question, if something is bigger than that, right? And that produces naturally a very linear decision boundary. In actually every other tree here has linear decision boundaries. Even the ensemble has linear decision boundaries. So my answer would be that, in fact, decision tree does produce linear boundaries, but when you make an ensemble of many decision trees, then the boundaries may not be any more linear. They will be so chaotic here. For example, if you look at this elbow, and you have a lot of these elbows together, you will have a very hard time saying that this is a linear boundary. This will look exactly like some curvy shape. Short answer is that decision tree does produce linear boundaries, but combined with many decision trees, the boundaries can be highly, highly nonlinear. So thank you for Olga. Thank you, Olga, for asking such a nice question, because I think it's very important to know about this. Because I think, yes, the decision trees do produce linear boundaries, but when combined, they can do much more than that. Let me see if there are any, because we reached the formal end of the lecture, which is in half an hour, but I guess, okay, let me see, there is one more question. You can delete already answered questions. So my problem is that I cannot delete already answered question. If there's an organizer that is being part of this lecture and they are listening to us, me like praying right now to the organizers. Dear organizers, please delete already answered questions. I beg you. This indeed is a very good comment, and it gets upvote from myself as well, because I have hard times reading through the questions that are answered and getting to the actually new questions. There is one question that I see from Olga again, but doesn't seem to be answered by me. What is the general logic behind, I think I already answered this one as well. Okay, this one already been answered. So dear organizers, if you're around here, please delete the already answered questions. I can go to recent and see what were the recent questions, but overall it would be nice if we could delete the old questions. Or you yourself, guys, ladies and gentlemen, you yourself can delete your questions that were already answered, so that we can free up the space for questions that weren't answered, so that I can see what the other questions are. Thank you very much for asking these questions. So as far as I can see, although organizers did not answer my prayers, I don't see that the old questions are removed, but I don't see new questions either. So I see that most of the questions are answered, or so I tried at least. So I think I can slowly proceed to the second part of the lecture. We will make, as far as I remember, there is a break. Alina, are you around here? Can I somehow, I'm trying to figure. Yeah, so do we have a break and in half an hour, right? Is that?
Yeah, you can now have a break, or after.
After the. Yeah, so I think we will have a, so you guys, can you please, organizers, can you please delete the questions that were already answered, so that we mostly see the unanswered questions. And I think we will have a break in half an hour. We will move into the boosting methods, and then we will have a break, if that makes sense.
Yeah.
Okay, great. Thank you very much. So everybody who is online, our prayers were answered, and we will have a break in 28 minutes. But before that, let's proceed to the boosting algorithms. So boosting algorithms. So we have seen quite a few things that we can try, right? There are several things we can try. We have seen how you can bootstrap the data. It reminds me of this novel about a Duke of Münchhausen who was trying to pull himself out of the swan using his own mustache and beard. So this is similar idea that is applied in bootstrapping. We're basically trying to make more out of less. So what else can we do with less, right? We can use the mistakes, right? So since we are in the supervised learning regime, we can use the data that we have about the labels and somehow make most of it, make most of the good use of it. So let's get back in time to the very first decision tree that we have built. And we're working with all 5 points here, right? So the accuracy of this split, you can quickly calculate it in your head. The accuracy of this split is something around 4 out of 5, which is 80%, right? There is one unfortunate mistake that our decision tree has made. right? So here is this unfortunate mistake. What if we can build, and here's the question here, what if we can build the next tree so that it takes care of this mistake, so that there is no mistake like that in the future? So how can we do that? We can build a second tree. So we call this tree a first tree, and we build a second tree, and we pass on to the second tree the same data, but now we will use a score, importance scores. So for each of the data points in the data, we will assign importance score. Each point will have an importance score. And how do we decide on what are the importance scores are? So at the first tree, when we do the first modeling of the first tree, we assign equal scores. So all points are equally important for us in that circumstances. So let's say if each point gets score of 1, right? 1, 1, 1, 1, 1. Okay. So now when we evaluate the performance of the split, we have 4 points guessed correctly and 1 point missed, as before, because every point has a value of 1. Now when we pass on scores, then we create new important scores. We don't keep the old important scores, we create new important scores. So what's the concept? How do we decide which important scores do we pass on? We use the results of the first tree. Basically, we looked at the first tree, and we increase the scores of the points that were misclassified, and we decrease the scores of the points that were classified correctly. So for example, this red dot here, so we increase its importance because it was misclassified. So it was misclassified, and that's why we make it not 1, but 1.5. So you can see that it grew larger. How about the other points? The other points will actually decrease in their score because they're classified correctly. So let's take a look. So before we had all the points had equal scores, but now they will have lower scores because they are classified correctly, right? So we decrease their score by 0.5. So I have to say before we go on that this 0.5 and decreasing and increasing by 0.5 is fairly arbitrary. So you don't have to take it very close to your heart. It can be something else. And it depends on the specific implementation of the algorithm that you're using. Most often, so in the practice session that I have aligned with this lecture, if you use 0.5 in the simple example case, this will work fine. I think in more sophisticated cases, these weights depend on something. They depend on number of points, they depend on the magnitude of how many points were misclassified, and so on and so forth. So it depends. So don't get attached to the 0.5 value. So now we need to construct a tree taking these coefficients into account. So it's not a humdrum tree that we have constructed before, that we have built before. This is the tree that will be built on samples with different weights, on items with different weights. So the algorithm that we saw before was like that. Just pay attention that the first step, the 0 step, choose a random set of features, is only applied when we are working with random forest algorithm. Since we are now dealing with a regular decision tree algorithm, we are not going to use random forest. Okay, so we just end up having 2 steps, evaluating all possible splits and choosing the best split out of the possible splits. Okay, so these are the possible splits. There are 6 possible splits. You remember that they can be both-sided. And now we have to evaluate each one of these splits, but not in the naive fashion, but taking the coefficients into account. So let's consider an example here. So what do you think is the performance of this split. So I remind you that the arrow pointing up means that we predict blue on the right and red on the left. So this is the way. And how do we calculate the accuracy of this split? We'll calculate it as usual, but we also take the coefficients into account. So, so the accuracy of the split is 0.5 plus 0.5 plus 1.5, because these are the points that we have guessed correctly, and we combine them using their coefficients. So it's basically 2.5. And we divide by the sum of all points. So if we divide by the sum of all points, then we get 71.4% accuracy of the split. We remember that the mirror, that the reverse split is the mirror of this accuracy, which means we need to subtract 71.4 from 1. And then we get something like 28 something. Yeah, 28.6. So this is the accuracy of the reverse split. Okay. We do apply the same technique, we use the same fashion to assess the performance of each split. So here we go. And take a moment and check out the performances of each split to see which one we should keep, right? So which are the best splits we have here. And if you take a look and wait for a second, then you will see that there are 3 splits that are equally good. So these are the 3 splits that are equally good. And so we have a draw. So we have equal chances of these 3 splits being selected. And to go through this, we basically, again, toss a coin or roll a die. In this case, we roll a die because we have 3 splits. So we need a 3-sided die. So we roll a die and we select this split as our split. Okay. Now I check if there are any new questions. So I don't see any new questions currently. Still, Sirhi was the last one to post a question. Okay. Yeah, so we choose this split. Okay. Now, this is the tree number 1, just to somehow remind us. This is the tree that we generated from the samples with different importance scores, right? So this is the second tree. And now we take the second tree predictions and again, rescale the importance scores. So we pass on again the same data, but again, we change the importance scores with respect to the way how the second tree has performed. For example, this point, the blue point here, has been predicted correctly. So as last time, we decrease its value by 0.5, which means that it has now no value at all. It's basically 0. It's nothing. The point that was originally mistaken by the decision tree has now been correctly classified. So we can safely decrease its value by 0.5. And we now have 1 for this point. This point, to the contrary to the previous points, was misclassified. So we increase its score by 0.5 and it gets back to 1. The same happens to this point. We again increase the score by 0.5, okay? And now this point has been classified correctly, so we decrease its score by 0.5, we get 0 again. So this is the data that we, that we end up having. These are the scores. We have 2 points which were nullified. We don't care about them at all. And there are 3 points which we want to classify perfectly, right? And we built the third tree using this data. So there are, again, there are several possible splits, but we kind of see that this is the split that we need. It has 100% accuracy, which is perfect. So we end up having this kind of, this split. We will keep this split. So now let's reconstruct the sequence of events. So originally we had the original 5 data points with equal weights, and we constructed the first tree, right? And then we moved on to pass on this data, except that we have had different scores. So now we actually introduce importance scores based on the results of the first tree. We changed the scores and we built the second tree. Now we have the second tree here. The third tree was built on top of the points that were predicted by the second tree. So we changed the scores again and we built the third tree. So this was the third tree that we have constructed. And now finally we can combine predictions of these models, of these three decision tree models into one ensemble. This is how sequential ensemble is built. We have 3 sequentially built models, which are combined into one ensemble. We overlay their predictions, and we do perform the same majority voting as we used to perform in previous cases. And yeah, so this is how ensembling from sequential ensemble looks like. So each one of the sequential trees takes care of the mistakes of the previous tree, and in that way improves the performance of the joint model. Because if you think about the parallel ensembles, we have no control over what are the mistakes that the individual models perform. While here, we specifically emphasize that every other next tree is supposed to take care of the mistakes that that was performed by the previous model. So there are a few important considerations here. This process of learning series of models is called boosting. Right? So we use the errors of the predecessors to improve the sequential model. And this process is called boosting. In standard boosting, models are trained on their misclassified examples from the previous model. So there is no room for importance scores. So in fact, standard boosting is only working with the concept that I have misclassified this example, so I keep this example for the next tree, right? So the training data for my next tree is only consist of mistakes of the previous tree. But in the boosting of that type, so this is the ensembling with boosting, we do have importance scores. And this specific algorithm is called adaptive boosting, right? And you all may have heard about this adaptive boosting from the short name AdaBoost. So many of you might have heard about AdaBoost, which is a type of model that exists in scikit-learn. You can use AdaBoost in scikit-learn, and this AdaBoost scikit-learn model is basically using these concepts. So AdaBoost introduces importance scores that are either decreased or increased depending on the prediction. So exactly how we did it here. AdaBoost, as a rule, uses decision trees of depth 1. So these decision trees are called decision stems, right? So these decision trees are called decision stems, and these are the types of trees that AdaBoost is using. Now I'll get back to the questions and see if you guys have asked any more questions. Unfortunately, no, you haven't really asked any questions. But I think I would like to make a break here. And dear organizers, oops, sorry. Can you tell me when do we go back by the schedule? Is it the half an hour that we make a break and then we go back? Organizers, Alina?
1 second. I'm checking the information. So we're gonna have like a break for 20 minutes, right? Or what?
You tell me. guess we can stop sharing and stop broadcasting right now, and come back and so yeah, now we are waiting for the answer. When do we come back? In the meantime, please write your questions, and this would be a great time to fill in with the questions. So I have 9 questions at the moment, but I guess most of them are answered. So I don't have more questions, or so it seems that I don't have more questions.
Actually, we're going to have a break for 15 minutes from now.
15 minutes?
Yeah.
Okay, but the lecture ends at 3, right? So it means that the second half will be like 3 hours?
Yeah, probably.
Okay, let's stop the sharing and broadcasting. Then let's get back at, what is the time now? Okay, at 1:05, right?
Yeah.
13:05, okay. Can you stop broadcasting?
Actually, only Alina can do this, but she is not here.
So we are live. Well, we were all this time, but hopefully you people got some.
Yeah, just a moment.
So I hope that everybody got the chance to grab a coffee or tea and joined our broadcast, joined our lecture. I would be pretty happy if you could, send the link to somebody from the summer school that you know that they're not participating. I think could be something that they might be interested in. So now we are getting back to our ensembles. So welcome back to the lecture about learning ensembles, ensemble learning. We just had immense pleasure to learn AdaBoost, to train AdaBoost on a very small example using decision tree stamps, which are, as the slide tells us, I hope that you guys, by the way, can see it. Just checking that everything is in order. Yeah. Alina, can you see my slides? Is all good?
Yeah. Okay.
All right. All right. Good. Just to remind you all that we have questions that you can post, right? So please post questions. I asked the organizer to keep an eye on questions, and as soon as the question was answered, to remove them so that it's easier to keep track of the questions that were not responded, that I did not respond to. So hopefully we will have this process sorted out. Now that we have built AdaBoost algorithm, we take a ride in the DeLorean car back into the future, where we have not built the boosting algorithm yet. So we travel back to the original data. So imagine that we haven't used any of the algorithms before. So this is the way how the data looked like before we applied a boosting algorithm. And this time we will build a new boosting algorithm, another boosting algorithm, not AdaBoost, but something else. And in order to do it, we will treat the problem this time as a regression problem instead of classification problem. So previously we had class labels for each of the dots. So we had ones and zeros. But now we will consider these ones and zeros not as a class labels, but as a regression targets, okay? So we don't have any more blue squares or red circles. We just have regression targets, okay? So these are now continuous values. Let's see how can we build the regression tree using these regression targets. Okay, so we use X1 and X2, both features, to build a regression tree that predicts ones and zeros as the regression targets. Okay. We use the same two methods, just the same two steps as we have employed previously. And as a metric of success of the tree, we will use mean squared error, right? Something very common to use in the regression problems. So here are the possible splits along the, with respect to X1, and here are the possible splits with respect to X2. Now for each of the splits, we will calculate the MSE, right? So how do we do that? Basically, here's our split. In one part of the tree from the left, let's say, we predict, in both parts of the tree, it's either left or right, we predict the average of the labels, right? So since on the left of this split, there is just 1 point, the average of this point is 1. So we predict 1 as a regression target for all points that are to the left of this split. This is the most optimal. To the right, we predict the average of all these points. And if you sum them up and divide by 4, then 2 by 4 will be 0.5, basically. So for each point to the right of this initial split, we predict 0.5. This is how the regression regression and decision tree would work, okay? But now we should calculate the MSE of this split. So think about this for a moment yourself. What is the mean squared error of this split? It's actually quite simple. We basically subtract the real value from the predicted value. We take the square, and then we take a mean of these differences. So for the first value, it's easy. 1 minus 1 is 0. Squared 0 is 0, so there's no problem with that. But with the right-hand side of the split, it's a bit more complicated. Well, just tiny little bit. So here's the formula. The first part of this formula is this 1 minus 1 squared is this simple part, which is a point on the left of the split. We predicted 1 and the real value was 1, so the square of this difference is 0. Then come points that were on the right of the split. So that is the first point, 0, which contributed 0 here. And we predicted 0.5. That's why we subtract 0.5 from 0. And then we take a square of this, which is basically 0.5 squared, which is 0.25. Then we take the next point, which is 1. We subtract 0.5, again, square it, and so on for each of the points on the right side. Okay, so what's the value here? So we simplify the expression. We simplify the expression further, and then we get 1 over 5. So this is a 1 over 5, which is 0.5, is the MSE of this split, right? So this is a mean squared error of this very particular split. Now we do this, we calculate MSEs for all splits that we have seen, okay? So the next split has a MSE of 0.23. The next has 0.23 again. And the last one with respect to X1 is 0.15. The same happens with the horizontal splits, 0.23 again, and 0.2. Now we got to choose the best split out of the ones that we have just calculated, okay? So we look at the splits carefully and we look for the smallest mistake. So when we did accuracy, when we built classification decision trees, we were hunting for the highest value of the accuracy of the split. Now we look for the smallest because the MSE is a measure of error. This is how much we are off the target. So we want to be off as little as possible. So in that case, we're looking for the split 0.15. Okay, this is the best split of the available splits. Now let's visualize the predictions. So normally in this point of the lecture, I would ask my students to tell me what would be the predicted value of the right-hand side and the left-hand side. But since I don't have, unfortunately, the direct access to you guys, I will do it myself. So to the right, we have just 1 point, and the point value is 0. So we predict 0, which means, well, we just predict what we see. To the left-hand side, we have 4 points. 3 out of 4 points have value 1, label is 1, and the 4th point has a value of 0. If we take average of these labels, we get 0.75, which is the most optimal predicted value. So by the way, the color here represents like some kind of strength of the prediction. The darker red, the higher the value, and more it is yellow and transparent, less value there is. Now we calculate the error. The errors, meaning that we calculate how much off for each label we were. So we look at the, for example, the first point. So we were supposed to predict 1, but we predicted 0.75. So the error would be 0.25, right? So this is by how much we were off the target for each specific point. And now we do this for each of the points in the training data. All right, so for the next point, we compare 0 to 0.75. And now we were much more, we were off by a larger margin. We were off by actually minus 0.75. Okay, that's the value by which we were off the target. Then there are 2 points which have onces, which means there are 0.25. Mistake is 0.25 for both of them. And for the last one, we have no error at all because we were not supposed to predict 0.75 for this point. We were supposed to predict 0, and we predicted 0. So we calculated the errors. Just to remind you that this is initial data that we had. This was the initial data, right? We had zeros and onces. And then we made a first prediction with the first 3, right? And these are the residuals, right? So they are called residual signal left after the first 3. We had 0.25s and minus 0.75 and 0. Now you can probably already guess it. We will use these residual signals as a target for the second 3, right? So we will use these as a next goal. When we will build a tree, we will try to predict these values, not the original values. So we train the second tree on these residuals from the first tree. Okay. Here we go. I will spare you and will not force you to calculate with me all the splits and mistakes and so on and so forth. So you have to just trust me on this, this being the most optimal split, and these would be the predictions. Okay, so this is the second tree that we get with a split of MSC 0.11. So the pinkish note up there, 0.11, is MSC of the split. The split is around 2.5, but the MSC of the split is 0.11. The prediction values on the left is minus 0.25, and the prediction value of the right-hand side is 0.167. Right, so this is the second tree. Now, again, as the last time, we look for the residuals, meaning that we look for the difference between what we have predicted and what has been there in practice, in reality. So we look for the differences between points. For example, if we subtract 0.25 from minus 0.25 from 0.25, it will be 0.5. And this would be the new target for this point. So these are the new targets: 0.5, minus 0.5, 0.08, 0.08, and minus 0.167. Okay, so these are the new targets. And these are the predictions made by the second tree. Now we feed this a residual signal into the third tree, right? So we create the third tree. So here's the third tree. The MSE of the third tree is 0.045. The prediction on the left side is 0.5, and on the right side is minus 0.125. And if you remember, so let me remind you what were the MSEs of the first, second, and third tree, right? So the first tree had a MSE of 0.15, the second one of 0.11, and the third one had even smaller, 0.045. You can see that MSE is decreasing, which shows us that we are making progress with our trees. The trees learn to compensate for the errors of the previous trees, okay? Yeah, so here the residual signal after the third tree, and you can see that also the residuals get smaller. They get smaller and smaller and smaller. And just to wrap this part up, so we could remind ourselves what was happening. This was our first tree. We predicted 0 on the right side and 0.75 on the left side. Then we fit in the residuals of that first tree into the second tree. And this was the tree that we got. And this was the last third tree of the series. Okay, so these are the sequential ensemble consisting of 3 trees where we treated the problem as a regression problem rather than classification problem. Okay. Now, I remind you that we have questions. Please ask me questions in the Slido that I could reply, and we can have a connection between us because I can't see you, and you might be very unhappy with what I'm saying, but there is no great way for you to communicate your frustration besides to write a question and say, hey, what do you mean by that, right? And I'll be happy to reply. So now that we have all these 3 decision trees that we have built, these are regression trees. I just want to emphasize this. We can get back to the original data, and these are the original points. And we are in the inference mode. So in the inference mode, we sum up the predictions by individual trees, okay? So we basically take the predictions of individual trees and we sum them up for the corresponding areas. Let's take a look. So here are the boundaries. These are the individual splits by all 3 decision trees, okay? So each one of them belongs to one tree. Now, each one of these smaller areas, there are 4 smaller areas. This one, this one, this one, and this one. So there are 4 areas, and each of these areas will have its own prediction value based on 3 decision trees that we have built so far. Let's take a look on the way how we how do we infer these values. So let's first consider the rightmost area. And these are the, up there at the top, you can see the corresponding areas in each of the trees, right? So each tree has a corresponding area. We look at these predictions and we sum them up for this area in the ensemble, okay? So in the ensemble, this area will have a value of 0.042, which is a sum of the predictions made by 3 decision trees above. Then we move on to the second area. We again sum up the predictions made by the trees, right? And we predict the value inside this area of that sum, okay, 0.792. The same happens with the third and fourth areas. So this is the third area, which is 0.475, and the last one is about 1. Okay, so this is the final decision map, I would call it. Decision, these are decision boundaries, decision map. So this is how much we predict, how much score, what is the score that we predict for each of the areas inside the final ensemble. So I'm seemingly not connected actually. Sorry for that. I'm trying to connect. Give me a second. I think I'm experiencing some problems. Just a second. Since I'm using another computer to look for to check out the questions, I just noticed that the computer for some reason got switched off. And this is not something I was considering. Okay. Unfortunately, somehow takes time to understand it's a problem. Now I should be connected. I'm sorry if you posted questions. I'm really sorry for that. Okay, I don't see any questions right now, but it seems that I'm back. I am back online. And this seemed to be back. Okay, please let me know if you have any questions. All right, so we have collected the results, right? So these are the this is the ensemble. This is how we built the sequential ensemble. But remember that initially we were actually working with the classification problem rather than regression problem. So how do we now go from these regression targets like 0.792 back into classification realm? So one idea is that we can use a threshold. Something like 0.5 is very arbitrary. We have 2 classes. So what happens if we have 3 classes? Then the things will get messier, and then we would need to predict more than 1 value. But if we have 2 classes, we could, for example, threshold the predictions by, let's say, 0.5. And then we will consider everything that is above 0.5 as class 1, which is blue, and everything that is below 0.5 as red, which is 0. And this is how the classification map would go, right? So if we would highlight the original cases, they would be like this. And you can see a very good overlap, meaning that blue squares on the blue area and the red circles are on the red area. And if you ask me why the hell the red areas are red and blue areas are blue, I will just tell you, well, we just thresholded the prediction values by 0.5, meaning that 0.792 and 1 became blue areas, meaning that every dot that is that falls into the area is predicted as a blue dot, and every one that has a value of less than 0.5 was considered to be a red area. And that's how these things turned out to be. These are called gradient boosted trees. Gradient boosted trees. So these trees are called gradient boosted trees. The algorithm itself is called gradient boosted machines or gradient boosting, right? So this method of learning is called gradient boosting, or sometimes as gradient boosted machines. Just to give you one little caveat is that you don't have to use decision trees. These models can be any model or almost any model that is fit to output probability scores. So every model that has a probability score or can provide a probability score can be used in principle as part of the sequential ensemble or as part of the gradient boosted machines. Okay. Now there are no questions so far. So GBM, the gradient boosted machines, is a basis for another very famous algorithm, which is called XGBoost, and which is developed by Tianqi Chen. And XGBoost is often considered to be the coolest guy, the coolest kid in the toolbox, right? So you might have heard about XGBoost many times. Many people consider this to be one of the key key methods for the Kaggle competition. So if you have ever participated in data science competitions, you might have heard about Kaggle. And in Kaggle, many people consider XGBoost to be one of the primary sources of success besides deep learning. So of course, many people use deep learning these days, but XGBoost is more lightweight, perhaps easier to train without GPU, and supposedly provides a competitive performance. Yeah, I just have to say that there are some caveats, some differences in XGBoost. It uses regularization term, comparing to plain GPM that we have seen in the slides. XGBoost is not that simple. It's optimized in C and also uses regularization. All right, so let's recap both boosting algorithms. So we have LvDS, which uses sample weights to estimate misclassified examples, right? So we have tree number 1, which was built on original samples with equal weights. Then we built a tree number 2, which now have different weights because we now assign important scores based on the output of the first tree. And the same happens to the tree number 3. We reassign the scores based on the results of the second tree. And then we model, so we build each model based on the new set of important scores. So the gradient boosting is different from LvDS in a very important respect. It treats the problem as a regression problem, not as a classification problem. So instead of dividing points into classes, one and the other class, it actually turns the problem into the regression problem. And then it predicts the scores, it predicts the values of points, and calculates residuals, and uses these residuals or differences with predictions as a basis for input of the second tree and third tree and so on. Right, so we can have more than 3 trees. So this is just an example. By the way, if anybody have a question about this, I have 3 trees or mostly 3 bags because of the slide limitations, not because of the some kind of magical number being 3. No. So you can have more than 3 trees, you can have more than 3 bags, and you can have less than 3 bags. So it's up to you. Yeah, so both methods, both of these LvDS and GBM are trained sequentially, one model after another. And these are the classes of sequential ensembles. Here's what we have seen so far. We have seen basic ensembling, we have seen weighted ensembling, and we have seen bagging, right? So when we use bootstrapping to create parts of data that we train the classifiers on. We have seen how the random forest works. We have tried LvDS and GBM. We have looked at LvDS and GBM. And now we venture into the last topic of today's lecture, into blending and stacking. So blending and stacking turned out to be, by the way, everybody, please, if anybody is listening, write some question so that I know that somebody is alive and still around, because I can't see any questions. Hopefully, this doesn't mean that something is broken and we don't get your questions. So if you're still listening, please put in some question. It doesn't matter what is exactly the content of the question. We can come up with something. Blending and stacking. So these things, they turned out to be quite useful in many applications. And after I found myself explaining stacking to one of my students, I figured that it's such a powerful concept that supposedly should be taught in universities, but we seem to lack this understanding. So I thought that this would be a good idea to add it to this lecture. So what's the point of the stacking and blending? What's the purpose Remember I told you that we can use cross-validation to decide the model weights in the weighted ensembling. When we discussed the weighted ensembling, I said that we cannot use test set because then we will compromise the test set. So we can use the CV to decide the model weights. And as it turns out, it might not be the best approach because it assumes that models will always perform according to these scores. So you do cross-validation on the training data, but then you still kind of apply these models to the unseen data. So you may not guarantee that the scores that you got with cross-validation on the training data will do perform the same way in the unseen data. So instead of doing this, I have to say that model performance may still vary because if you don't have enough data for the cross-validation, then you may have very unstable estimates, which will lead you to probably somehow overemphasize differences. So what can we do instead of using CV? Well, we can still use another kind of data, another data set. And we can train a meta model, something called meta learner on top of the models that we have trained originally. So on top of this model 1, 2, and 3, we can train a meta learner. Let's take a smaller example when we have just model 1 and model 2, okay? We use model 1 and model 2 to predict probability of the class dog of each image. Okay, very simple. We have cats and dogs on images, and we use both models to predict what is the class of the image. Okay, the resulting probabilities we will plot on this graph here. On the x-axis, we have M1. So what's the probability of a class dog from the model M1, sorry. And model M2 probability will be shown on the y-axis. Okay, so these are the meaning. Probability of class dog based on probability outputted by M1 or M2. So both models predict both probabilities, dog and cat, but we will only use dog here. So we are only concerned with the probability of the class dog. So we don't really look into the class cat right now. So let's take an example. Here's the first image of the training data. We pass it through the trained models, and we get the probability. Okay, the probability of this image being of class dog by model 2 is pretty high. It's 0.8, and it's not too high by the model 1, so it's 0.4. So this is where this point will be located on the graph. Okay. We take the second picture and we fit it into the models. And now the first model is saying that this is a very likely to be a dog. And the second model is unsure, it's not confident. And then we fit in all the other images and we collect the data. So we collect this information about how models think about different classes. And we can see that there are some patterns. There are some things that we can note here. What in fact happens is that we can train a next level model or this meta learner on top of these probabilities to decide the class of the point, not based on the probabilities per se, but based on the way how they acted, how the models acted in the past with respect to the real classes. So we use the probabilities, but we don't have a fixed threshold like 0.5 like we usually have in the machine learning. But, and we don't have majority vote or weighted ensemble. We actually use a decision tree to decide the class, okay? And the good thing is that we can interpret each one of these areas now. So for example, this area is the area where M2 model is very confident that the image is dog, and M1 is not confident. This model, this is the area where M1 model is very confident that the image is dog, but we saw from the practice that model 1 is very, very inaccurate. And this is where these kind of models that somebody asked in the previous part of the lecture, that what happens is the model is counterintuitive, right? So it's counterproductive. It acts counter to the general logic. Okay, and this is the area where both models are confused. So we saw that basically, if model 2 is confident that the image is dog, we should go with the model 2 decision. If both models are confident, then it's probably cat. And if only M1 is confident, then it's also cat. And if both models are confused, then probably cat. So this kind of decision tree would not be possible if we would have some fixed threshold, right? But since we trained meta learning, we now have this kind of more sophisticated way to decide the class. So training additional model on top of the ensemble. So we do have ensemble of 2 models, and we train the decision tree on top of these 2 models. We call it stacking, right? When we stack models into the tower of models. Okay. The stacking model can be any model. So it doesn't have to be decision tree. It could be another deep neural network that you can stack on top of the previous 2 deep neural networks. But you have to ensure that this other deep neural network has enough input width, because we all know that deep neural networks work with a lot of data. And since these points are very shallow, they are just 2-dimensional points, the deep neural network may not be as good as some other more simpler models. There is one problem, however, with the whole setup that I have shown you. We were using training data and to predict for the meta learning. So to train the meta learning algorithm, we were using training data, which is not good because models have already seen the training data. And therefore, they're probably the probability scores are fairly well overfitted. They are pretty sharp. Models already have seen this dog and this cat, so they know that this probability should be large and this one should be small. So it probably is not very good. It's not a best practice to learn meta model on top of the overfitted probabilities, because this will not be the same when we take not a training data, something else. Therefore, people use something like CV-like approach, cross-validation-like approach. They divide the training data into folds again. Then they train models on several folds. And they use the third fold or holdout fold as the basically training data for the meta learning model. Okay. So these are different folds. We use different folds, and then we predict the holdout data, and we collect the data for the meta model. Okay. So this is called classical stacking. So I still don't see any questions. I hope that everybody has a link and everybody is following. So this is called classical stacking approach, right? So this is classical stacking when we use a cross-validation-like approach to collect data for the meta learning model. The non-classical approach is called blending. It's when you basically split the data into folds and use one separate fold for validation. And you don't really do this meta learning. So instead of, you take part of the training data, you train models, and then you take part of this holdout part as a validation data, and you use it as a training data for the meta model. So this is something a little hard to comprehend at first, but once you give it a try, then it will work much better. For me, it seems as if stacking is more appropriate approach in most of the cases. So I would I would prefer stacking to blending, because I think stacking provides more. It uses data more efficiently. Okay. All right, so we have seen all the things so far. So we have seen basic ensembling, weighted ensembling, backing, random forest, boosting, and now we have also checked the stacking and blending. In principle, we could use something like this. We could have original data, then we can have bootstraps. We can do some boosting on top of the bootstraps, use some other boost on top of each of the boosting, on top of each back. And then we can do some stacking and blending. Okay, so here is a visualization of how cool this approach comparing to the other approaches. It's a structure of the atmosphere of the Earth. So the first layer is troposphere. It's a stratosphere that follows. Then it's a mesosphere. Then it's a thermosphere. Then it's an exosphere. And here goes this stacked ensemble of backed boosted trees, right? So this is as cool as space, all right? But as we have discussed previously in the questions, great power comes with a lot of responsibility. So what ensembles are good for? They're good for winning competitions. They're good for getting the best out of the data as possible. So they can be very efficient and the performance can be very good. At the same time, they still can suffer from overfitting. So there is no silver bullet against overfitting. And you saw that, for example, in stacking, it's very easy to get into this overfitting state. Training monsters like this may take a lot of time. So it's a fairly complicated and very slow process, or so can be, unless you use something like XGBoost, but then you can have ensemble of XGBoosts. So there is no problem with that. And the next and probably the last thing that I wanted to say is that ensembling may compromise interpretability of the model. So you may have ensemble of ensembles, but then the problem is that you may not be able to trace back the decisions that your model has made. Okay, you may not be able to understand why the model made the decisions it made. Here it goes this very general joke about, is this your machine learning system? Yep, you pour data into this back pile of linear algebra and then you collect answers on the other side. And then what if the answers are wrong? You just stir the pile a little and then they start looking right. Okay, so at this point, I don't have, oh, I have tons of questions now. Okay, fine, great. So I'll attend to questions and then I'll get back to the, we'll have Kahoot. Somebody wrote everything is clear so far, and that person gets a vote from me automatically. Thank you very much. How are these boosting algorithms sensitive to outlier MSE for decision? Does it require some processing of data? So the question is, do boosting algorithms, let me go back to probably to some slides back. Okay, this one. Are they sensitive to outliers in terms of MSE? For example, if we are talking about regression, if we're talking about GBM, for example, MSE is considered to be sensitive to outlier values because if there is a very, very bad prediction, then the entire tree seems to be very, very bad. Yeah, they are. In MSE is sensitive, but you can use RMSE or some other metric like MAE or something like this to kind of build the robustness against outliers. I don't think that these algorithms are particularly sensitive to outliers because as you can see from bagging, for example, if you think about the random forest algorithm and you think about bagging, right? When you select a random set of data, not all the data goes into each bag, but some random set of data goes into each bag, then it's likely that some of these, as you are saying, outliers or misleading values will end up in this missing part, and your bag, your decision tree will be built with respect to the correct data rather than the outlier. So there is a good chance that some of the trees that you built inside the ensemble will still be good and performing well. So I would say that it's not particularly sensitive to outliers. But thank you very much for a good question. Let me see what is the, okay, Bogdan wrote, how do we decide when to stop? How many iterations we need for building final classification map? Or do we always stop at number of, so Bogdan refers to number of trees that I have used so far, which was 3. So the question is, how do we know, if we go back to the, I will stop here. So if we look at the sequential ensembles, for example, then Bogdan is asking, how do we know when do we stop training the trees? Okay, what if I want to train like hundreds of trees, right? I will get very good performance probably. How do I know when I stop? Okay. So my answer would be, first of all, you are bound by the technical requirements. So in the sense that training 100 trees will take you ages to complete. So this is something you probably want to avoid. Secondly, you have this, you can always have a threshold on what's the residual error. For example, if we are talking about ADA boost, you can think about this as long as I have correctly classified all 100% of my data, I want to stop there. Or if I classified 95% of my data, I want to stop there. I don't remember exactly, so in scikit-learn, in my practice session, I definitely know that there is a default number of trees that you built. So it's not adaptive. It's not that it thinks, okay, now I can start. It actually has a default number of iterations. I think the default is something around 3 or 4. In fact, you can check it out. You can check out the scikit-learn implementation. But yet another thing is that this number of iterations is a hyperparameter that you can tune as any other hyperparameter, for example, cross-validation algorithm. In using cross-validation algorithm, you can build different types of ensembles. And then using cross-validation, you can decide which is deeper or more shallow, which one performs better. So I think the answer is that there are technical limitations. You can decide the level by the cross-validation, the depth of your sequential ensemble. And it's also default parameter in scikit-learn. I think there is some kind of fixed number of trees that they built. So thank you, Bogdan, for replying, for a question. I will put a like as well. Can we use, so Sergey is asking, can we use in prediction inference other aggregation functions apart from sum? So, so as far as I understand, Sergey refers to the GBM. In fact, he refers to the part when we sum up the predictions based on every tree. I think, as far as I remember, sum is the default version. I think this is what happens. And if you think about this, I think it kind of makes sense that you predict the residual, which means that you gotta be predicting smaller and smaller margins of values with each additional tree. And it kind of makes sense to sum them up, especially provided that some values could be negative and things like this. So I am not aware, the honest answer here is that I'm not aware of other functions that people can use and when they sum up the GBM performances, when they aggregate the performances. But yeah, but that's a very good question. Thank you for asking this one. Roman, can we hear and see you clearly? Keep up the, okay, thank you, Roman. I just upload this one. No specific questions from Roman. Roman, but you got my thumbs up. Thank you very much. How can we perform a multi-class classification using GBM? I think this is a very good question. Whoever was the person to ask this question, thank you very much. I appreciate your question. Indeed, this now gets very complicated since you have now 2 classes or 3 classes or 4 classes to care of, right? So it's not it's not easy anymore to decide which class you kind of refer to. And moreover, I'm not sure I know exactly how this is done. Okay, I might assume that you might go for the binning, right? So when you predict a score, if your final score falls into a specific bin, let's say let's take our example. Let's say that we, instead of 2 classes, we have 3 classes, right? So now instead of having 0.5 from 0.5 to 1 being class 1 and from 0 to 0.5 being class 0, we have from 0 to 0.33, which is first class, and then from 33 to 66, which is a second class, and so on. So I might assume that, but being honest here, I don't know exactly how this is implemented. So this is a very good question. I wish I would know the answer for, but sorry for that, I don't know. Kostya is asking, how to decide whether to use just threshold or train tree forest on top of scores? Oh, I can see one hint. If there is too little training data, we wouldn't be able to be fair here. But what if enough data? I would think that tree would always be beneficial, but on practice, it's not used often. In practice, it's indeed not used often, but I think it's there are different reasons for why it's not used often, because it's more complicated. It's always easier to just threshold it and say, hey, more than 0.5 is good. But, and also in practice, why it may not be used often is that there is not always such a big need to go so high performance. So this is one of the things that I think is not good about ensembles, that they give you the small edge of performance, but in fact, I think they, not always you need this additional 2-3%. So it's not always worth the trouble. That's the truth. And it's not always worth the trouble to train a meta model and make sure that you're not compromising the training data. So all these things that we have just discussed require care and attention, and it's not always worth the trouble. So I think that's why it's not always used. But I think if you train the decision tree on top of your scores and instead of threshold, of course, it should be more beneficial it should be noted that if there is a possibility for this. So if the models are sufficiently different and there is a way to kind of get to squeeze out better performance out of this. But thank you for asking this question. Sergey, is interpretability about explaining model with human words? Many math problems are solved with abstractions, no words, so should be problems of machine learning. Am I right? So indeed, Sergey, I have to tell you, with all this GDPR kind of fuss around GDPR and us meaning machine learning practitioners, not being able to explain what neural networks do, it's a bit controversial here, because we kind of know what neural networks do, but would it make sense to a lay person, to a public? No, probably wouldn't. If we would just tell them that you multiply matrices in that order and that this is how you get this response, what they want to know is exactly why the model thought is the way how it is, right? When we think about the medical field and you are building a diagnostic model, then what people actually want is to know what part of my X-ray or what kind of aspect of my X-ray made this model think that I have cancer or I have a tumor in my lung or something like this. Then they want to know in human words. Yes, interpretability is basically an ability to explain the model decision in human words. There is another competing term besides interpretability. It's called explainability. And they are somewhat similar, but somewhat different. But basically, if somebody's saying interpretability or black box, they refer to this absence of human word explanation level. So thank you for asking a question. Pitfalls of Ensemble. Any anonymous person is not convinced by the pitfalls. So I think the pitfalls are very simple. So you lose interpretability, you build a large black box. even random forest itself, which is an ensemble, sometimes considered to be an open box. So you can open the random forest, but it gets harder. If you build very large ensembles, then it gets much harder to interpret. And if you don't use decision trees, for example, as your basis for the ensembles, then it gets very, very complicated to actually infer useful explanations, right? So a decision tree is good because you can say, well, if this, then I decide that. In these kind of models, it gets very, very complicated. So it's interpretability that you lose. Secondly, there was this question by Serhi, is that why don't people use this? Or was somebody else? I'm not sure. Somebody was asking, why don't people use this? Because it's a trouble. It actually makes you think hard, and it takes you time to actually build this kind of pipelines that do make justice to data at hand and not overfit. It's easy to build a metadata on top of the training data predictions, but then you wouldn't get a nice performance boost because you will be overfitting to your training data. So it's a trouble, and it's hard. Sometimes you just don't care about this 2 additional %, or 1 additional %, or less than 1 additional % of performance. So it may not be worth the trouble. Given that there are a lot more things, like you need to look for the diversity of the models. So the models should be diverse enough. But so far, however, despite all these things, the best models that win the competitions tend out to be ensembles. Very large, very complicated, very hard to train ensembles. So pitfalls are basically all these small things, like is it worth the trouble? How much time it takes? Do you care about interpretability? Yeah, these kind of things. I would say that these are the main pitfalls, if I understood what pitfalls are. Yeah, so thanks for asking that question. Now I want to propose to move on to Kahoot. Right, so I have a Kahoot quiz prepared. Let me stop sharing for a second. And so let me start the Kahoot. Okay. Let me share the link with you guys. So if anybody, So there is some discussion about Slido. I'm really sorry, I didn't see that one. So you should go to kahoot.it, and I send the link. And Pim is so I just sent it to the Slack. Everybody, I just sent it to Slack. Please do get in. I will share my screen with you guys, so you can. I will take on this here. I'll share my desktop too. Okay. So currently we have 0 players. So if you guys, let me show you this one. Okay, we have 1 player. Great. So if you guys go into Slack and you type Kahoot it and you enter the pin, you will be among Obi-Wan Kenobi and Roman R and Cube. You will join them in venture in the competition for the best. Well, basically the title of the Ensemble Learning Expert, Master of Ensembles. We are basically going to compete for the title of the best ensemble master alive. So now there are actually 9 players. That's very good. Does anybody else wants to join? 10 players. I will stop. I will basically start the competition in, let's say, I don't know, a few minutes, 1 or 2 minutes. I'll just add the channel tag to this message. While you guys are adding yourself, I'll see if the adding will stop. So let's just channel it. Okay, 14 players, 16 players. Okay, let me see. I'll have a stopwatch here. So it goes like this. Oops. Until 1 minute. So you have 50 seconds. Okay, basically, okay, 17 players. Serhi, welcome. I don't see Olga. I hope Olga is around here. I saw that somebody wrote a question. Link is in the Slack. You guys, everybody is in the Slack. I also can, I'm also sharing the screen, so you should be able to see the pin. So this is all you need. You need to go to kahoot.it and enter the pin. So I hope that you guys can manage that. While you still do it, and we have 10 seconds. So Raman is asking, what about ensembles in production rather than in competitions? I would say that in production, it's a rather rare beast. I would say that in production, we usually compare to the ensemble just to see how well we do comparing to the, by default, better model. Okay. Yeah, right. So let's get started. We have 19 players. It should be enough to get started. Now you should check out my screen. So this will have a question. Ensemble learning is often compared to regularization. What kind of regularization? So ensemble learning is compared to regularization. What kind of? Early stopping, dropout, implicit, like augmentation, or explicit regularization, like L2 regularization. So don't worry too much. These questions may not have been in the lecture slides, but these are just to kind of check. I hope that you guys can reply. So just go ahead and reply something. It's not so important. The title will definitely be somebody's, but we will know this. We will not know that person in person. So don't worry about this. Just go ahead and click something. And I will try to explain why do I think that the right answer is the right answer, because I may not remember exactly right now. So what is it? What is it? Early stopping, explicit regularization, dropout, or implicit regularization. So what is it, the ensembles? And I can show you the book where the answer is written. So the answer is right here in this book. It's Deep Learning by Jan Goodfellow. And in this book, Jan actually compares ensembling to one very specific type of regularization. Okay, the last person, please click something. We can go on with our lives. Okay, you have 10 seconds. 7, 6, 5, 4, 3, 2, 1, go. Okay. So usually they compare the ensemble learning with augmentation or implicit regularization, right? So implicit regularization is when you give a lot more space for your models. You kind of give more models an opportunity to learn best. I may not, I actually, myself, I didn't remember that question. So if somebody is angry I actually would vote for dropout myself. So sorry for that. Currently, the leaderboard looks like this. We have a TensorFlow on top, or I'm hoping that I'm reading the nickname correctly. And then we have Suman and Patrick. Okay, let's see what happens in the second question. Majority vote is usually carried out by. So what is majority vote is carried out by? First, identifying the most superior model and adopting its prediction, asking models representatives, taking a mode of individual model predictions, asking for a show of hands. Majority vote is usually carried out by first identifying the most superior model and adopting its prediction. Basically, who is the alpha model in the room, and basically adopting its prediction. Asking models representatives, asking for a show of hands, or taking mode of individual model predictions. What is mode, I wonder? Think about this. 8 answers already. Uh-huh. 10 more to go. Seven more. Well, I don't know. Previous question was replied by 18 people, so I remember 19 people signing in. Okay, 16, 17. Go ahead, one person. Yay, 19. Okay, so a mode is the mathematical function that chooses the most frequent value, and this is exactly what the majority voting is basically doing. Asking for a show of hands and mode those representatives is correct, but it's not what majority vote does, right? So it's basically weighted ensemble. While majority vote percent is taking mode of individual model predictions. Okay. Right, we have a new leader, which is Suman 16. We have Patrick, and maybe R is Roman, who knows, maybe. The third question, what happens when models disagree on a class of data point? You remember this case when we had a dog, cat, and rabbit? So what happens when models disagree? What happens? They roll a dice or toss a coin to figure out the winner. Models argue fiercely until the true answer is revealed. They beat up each other until the true answer is there. Models train another model to vote that would break the tie. Models ignore the data point in question and move on to the next one. Well, that's a very classical approach. You just ignore the problem until it disappears. So which one? Do you toss a coin? Do you argue fiercely? Do you train a meta model? Or do you ignore it just to just leave it out? So 8 people answered. I wonder how many people would vote for the fierce arguments between models. Okay, 14 answers so far. Go ahead. 5 more, 5 more. Hey, go ahead, go ahead. 17, 18, 19, yes. Oh, there are 20 or something. Okay, fine, good. Yes, models indeed roll a dice, toss a coin, and then they figure out the winner. So the second most frequent answer was models train another model. No, but they don't do it by themselves. Let's say this is our decision. This is we who decide that we will train the third model on top of the meta model on top of the models. Somebody still replied that they argue fiercely, and somebody was unsure and they thought that we will ignore the points. Okay, we have a new winner. We have a new first placer, which is Patrick, and then R, which I don't know, maybe a Roman, and then Suman 60. Okay. Bootstrapping is similar to cross-validation in the following way. So the bootstrapping and cross-validation both apply randomness when selecting different parts of data. Both are used to diagnose overfitting. Both split the data into several non-overlapping chunks, and both use data that was not selected as a validation set. Okay, so what's the difference between, okay, that's not the difference, but the similarity between bootstrapping and cross-validation. Randomness, overfitting, diagnosis for overfitting, splitting data into several non-overlapping chunks, or use data that was not selected as a validation set. Easy peasy lemon squeezy, nothing to write home about. Walk in the park, piece of cake. Or so it should be. 6 answers. Very complicated question. No pressure, ladies and gentlemen, no pressure at all. Just the title of the Master of the Ensemble Learning right now is in your hands. 13 answers. Okay, not too bad. I think 5 more. Yeah, okay. Go ahead, click, click, click. Click, click, click. 17, 18, no, 18. Oh, take it easy, just click something. 7, okay, good. Indeed, both apply randomness when selecting different parts of data. Why yellow one is not correct? Because actually only cross-validation creates non-overlapping chunks, while bootstraps may all likely be overlapping. Why blue is not correct is that bootstrapping is not used to diagnose overfitting. Only cross-validation is used, and nobody voted for green. Okay, but majority was right. Okay, Patrick kept, I assume, his place. So TF is back to the top. Congratulations. Bagging stands for, very careful here, boosting plus augmenting, bootstrap plus averaging, boosting plus aggregating, bootstrap plus aggregating. So bagging stands for boosting plus augmenting, bootstrap plus averaging, boosting plus aggregating, and bootstrap plus aggregation. What bagging stands for? We have first answer. By the way, ladies and gentlemen, no pressure, but sooner you answer, more points you get, okay? So faster you answer, more points, higher your rank. Go, 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 go. Yes, this is correct. Just go ahead. Go with the flow. Listen to your gut feeling. Yeah, 16, 17, no, 17. 2 last. Click something, click something. What is it? Bootstrap plus averaging, boosting plus aggregating, bootstrap plus aggregating, boosting plus augmenting. Okay? Aha, 20 answers. Okay. We have one more person. Ooh, we have more than 20 people. Yes, indeed. Bootstrap plus aggregating. Remember bootstraps? We create bootstraps and then we aggregate. It could be averaging, could be majority. So it's not bootstrap plus averaging, but it's bootstrap plus aggregating. Congratulations to most of you. You were all correct. Well, most of you were correct. So Patrick R and TF are still top 3. AI is getting close. And you guys should be aware of Obi-Wan Kenobi, who is just on the back of the heels. Okay. Bagging is different from boosting in the following way. Bagging creates a parallel ensemble while boosting sequential. Bagging uses decision trees only, while boosting can use other models. Bagging creates a sequential ensemble while boosting parallel. In bagging, trees can only be of depth 1, while in boosting, no limit. All right, so bagging is different from boosting in the following way. What is that way? Bagging creates a parallel while boosting sequential. Bagging uses decision trees only, while boosting can use other models. In bagging, trees can only be of depth 1, while in boosting, no limit. Bagging creates a sequential ensemble while boosting parallel. So what is it, the difference? The bagging and boosting. Hey, 7 answers. We have 14 to go. The difference between bagging and boosting. Make sure that you select the one that is the difference. Hey. Yep. Good. Good. 5 more. 4 more. You guys have very little time left. Click on something. Better to click on the wrong one, not to click at all. So just click. Oh, time is out. Yay! It's indeed, bagging creates parallel ensemble while boosting creates sequential. So if you look at the media that was shown, so this is boosting, right? So it has sequential ensembles. It trains sequentially, while bagging creates parallel bags, which basically have parallel models. Okay, cool. Let's see who is first. Okay, AI became a runner-up. So AI is on strike with 5 correct answers in a row. This is significant. That's why you should click faster. And Patrick keeps his position, a top leader position. The main difference between bagging classifier and the random forest is the following. So the difference between bagging and the random forest. Random forest does not need to toss coins as often. The random forest is calibrated classifier while bagging is not. The random forest can grow more trees than bagging classifier. The random forest selects random set of features for each node in the tree. So what's the difference between bagging classifier and the random forest? What do you remember from the lecture? A random forest does not need to toss coins as often. The random forest is calibrated classifier while bagging is not. The random forest can grow more trees than bagging classifier. The random forest selects random set of features for each node in the tree. Yay! Click, click, click. Remember, the first one clicks, gets more points. So you should really click quicker. Click quicker, quick clicker. Yay, 16, 17, 18, 19. Yay, 21. Okay, we have more people than 21. Yay, okay. Indeed, random forest selects random set of features for each node in the tree. That was in the lecture. Random forest can grow as many trees as bagging classifier. There is no difference in that. Random forest as calibrated as bagging, so there is no difference in that as well. And does toss a coin more often than the bagging classifier, probably. Okay, the same tree. So everything is basically the same. Compute the accuracy of the split on the picture. Here is the picture. Please do compute accuracy of this split using importance scores. So be careful to use importance scores to calculate the accuracy. So how many were guessed correctly and how many were not? And sum them up and divide one by the other. So just go ahead. So this is not just a sum. This is not just a number, let's say 3, but it's also the corresponding coefficients. Okay, so what is this? The accuracy of the split on the picture. Okay, 15, 16, 17, 18. Yay, 20 seconds left. Jump in, 20 answers. Okay, 20, 2 more. 8 seconds, 7 seconds, 6, 5, 4, 3, 1, 0. Indeed. So if you look at the in the image, right? So there were 3 points that were predicted correctly. 2 blue points on the bottom side and 1 red point on the top side. So we just sum them up, we get 2. Over, so this is what goes into numerator. What goes into denominator is the sum of everything. So we just sum everything up. We get 4, so it's 2 over 4. So it's 0.5, indeed. Congratulations. Okay, we have a new leader, which is TF. I hope that it's TensorFlow. And Nikita has the highest climb, is the highest climber. He just got 5 places up. Congratulations to Nikita. A 9th question, how GBM merges predictions from individual trees to form an ensemble. It averages up the predictions by individual models. It ignores predictions by individual models. It adds up predictions by individual models. It multiplies predictions by individual models. So we have predictions by each model here and there and here. What happens here? Do we sum? Do we divide? Do we, what do we do? Take your time. So what happens when the GBM merges things into ensemble? Is it that it's add up, it's multiplied, it's ignored, or maybe averaged? Okay, go ahead. 17, 18, 19. 2 more, or 3 more, don't remember. Just click 20. No pressure. 20. Okay, 18 seconds, 17, 16. 5 seconds, 4, 3, 2, 1. Stop. Yes, most of you were right. It adds up the predictions by individual models. We were discussing this, I think, with Serhi, who asked this question, and he asked if, so I don't remember if who asked this specifically, but the question was whether there is any other function that can be used. So I'm not aware of these. I know that it sums up the predictions, but it could be that some of them are averaging, but the one that I taught in the lecture was adding things up. Yeah, let's see what happens to the leaderboard. Patrick is on the strike. 1 has moved up into the top 4. TF remains on the first place. Great, we have a very dense competition. AdaBoost, in contrast to GBM, treats the classification as a regression problem. True or false? You guys have 24 seconds to answer that one. Very quick. AdaBoost, in contrast to GBM, treats the classification as a regression problem. True or false? 15 seconds. 0 answers. Go ahead. Click something. 50-50 chance. Oh, only one person guessed it, and only 3 clicked. Yeah, it's false. Actually, GBM treats the problem as a regression problem, not AdaBoost. Okay, let's see if any of the leaders, none of the leaders scored anything. That's interesting. 11th question. So you guys pay attention. XGBoost is an extension of GBM, AdaBoost, blending, or bagging. What is XGBoost an extension of? I briefly mentioned XGBoost in the lecture. I said that it's, I think about the name of the method, right? So what is it the extension of? Yeah, 11, 12, 13. Should be fairly easy. Yeah, 18. 20. This was quick. Why didn't you guys reply the previous one? It was like super simple. 60 seconds to go. 2 more or 1 more person. 1 more person. 20, 21 right now. We want 1 more person. Yeah, indeed, this is GBM. XGBoost is a GBM on steroids in C and with regularization. Okay, a GBM with regularization and highly optimized is XGBoost. Okay, Patrick is on the 2nd place. AI is on the 3rd place, and we have Roman. Okay, Roman R is on the 5th one. TF is still leading. Blending has one advantage over stacking, and it is, oh, there is a delay between video and Kahoot. I'm sorry for that. Blending has one advantage over stacking, and this is speed. Blending needs to train models only once for a specific train set. Blending uses data more efficiently. Blending produces much more accurate models. Blending sounds so much cooler. Sorry, Valery, I can see your comment in the chat. I have little control over these things. I just can only suggest that you guys click as soon as possible on the option that sounds interesting and sounds good. I understand that since we are broadcasting and I'm sharing my screen, then probably there's probably a significant delay. I'm sorry for that. I'm hoping that this technical problem is basically equal for everybody, so everybody is in equal position. So it means that at least there is an equal opportunity. Okay, 15 answers, 16 answers. Okay, 17 answers. 17 answers, 18 answers. We are very close to the finish line, ladies and gentlemen, very close to the finish line. Indeed, we haven't really discussed the advantage of blending over stacking. What I said in the lecture was that I find stacking more data efficient, right? That's why it's not stacking, it's not blending that uses data more efficiently, but stacking, at least in my opinion. But blending needs to train the model only once. That's why it's faster, right? So let's see how many of you guessed it. Okay, AI, I guessed it and moved up one place. TF is still leading. 13th question. Training super deep stacked ensemble of back booster trees can be a good idea because. So because, why this could be a good idea? This will result in a very lightweight model that won't overfit. This will result in a very transparent model, very explainable model. This will result in a powerful model that will produce high variance. Still, this will likely result in a model that can help win Kaggle competition. So training super deep stacked ensemble of backed boosted trees can be a good idea because this will result in a very lightweight model that won't overfit. This will result in a transparent model, which is interpretable. This will result in a powerful